Salam everyone. So we are starting this lecture on the RF transceiver architectures. There are three lectures that are going to be taken on the same topic. And in each one of them, we will discuss part of the list that we see here. So we are going to discuss first some general considerations that leads to the issues addressed in different transceiver architectures. When we talk about transceiver architectures, we are talking about the transmitter and receiver architectures as well. So we'll start first with the receiver architectures, and then we will go to the transmitter architectures. Within the receiver architectures, we are going to discuss the heterodyne receiver, the direct conversion receiver, and the image reject receiver. And then last but not least, we will discuss within the transmitter architecture, the direct conversion transmitter only. Okay. In each one of those architectures, we are going to discuss the advantages and the disadvantages, mainly why this architecture was established, how does it look like, and then what are the issues in that architecture and how they are addressed. Okay. So today we'll start with the general consideration. An important thing to notice is that the whole dilemma of designing different architectures for transmitters and receivers comes from practical challenges or practical considerations, particularly the ones that has to do with the bandwidth filtering requirement. So the main concern that we will discuss here is what is the effect of having a narrowband communication system or a narrowband channel, a channel with a small bandwidth. The main issue with a channel with a small bandwidth is that at some point, as we see here, you will need actually to pick your signal and reject all the other signals around you so that the receiver can receive the correct information. Okay, so this means that if this band is narrow and the center frequency of the band is high, then we end up with the ratio between the center frequency and the bandwidth as a high ratio. And as you know from your studies in electronics and your circuits, that there is something called the quality factor of a filter, and that quality factor of a filter is proportional to the center frequency, FC, divided by the bandwidth. So the higher the center frequency, the higher the quality factor, the higher the bandwidth, the smaller the quality factor. Okay? Now, what does the quality factor represent? Again, the quality factor also is a representation of complexity of filter design. Typically, this complexity is shown in the form of cascaded elements. So the higher the quality factor, the higher the number of cascaded elements in my filter, which means that it's going to be more costly and it's also going to be more lossy because many stages, one after the other, each one of them is non-ideal, so we'll definitely have some losses. So more losses in my filter. Okay. So that's the situation. So basically, the idea is in order for us to select a particular signal in narrowband transmission, we typically need high quality factor for our filters design. Now, can we simply filter the interferers to relax the receiver linearity? Remember that the nonlinearity effects has good part of it related to if we have adjacent interferers, right? So can we simply just design our circuit to have higher level of nonlinearity, which means less quality in terms of the linearity requirement, by simply filtering out all adjacent interferers and working free of adjacent interferers, hence minimizing the effect of nonlinearity? Can we do that? So to answer the question that was asked in the previous slide, let's take this example and see whether it's really doable in terms of filtering out all adjacent interferers or not. So let's look at the problem. It says that we have a 900 megahertz GSM receiver with 200 kilohertz channel spacing. Okay, so basically, I'm going to try to draw this as we go through the description of the problem. So this is our frequency in megahertz, and we have a 900 megahertz GSM receiver. So our signal is somewhere centered around 900 megahertz. Okay, I'm not gonna use the okay, so it's centered around 900 megahertz, and then we have channel spacing with 200 kilohertz, which means that between each signal and the next signal in the same band, there is going to be a separation of 200 kilohertz. This means that simply around this signal, we have to leave from the center frequency a distance of 200 in this direction and a distance of 200 in the other direction. Similarly, for the next signal, same thing has to happen, which means simply that the next adjacent channel within this communication band is gonna be somewhere around, centered around double that 200 distance. So it's gonna be 900.4, right? That's a 400 kilohertz separation between those two, right? So the distance between this and this center is 400 kilohertz, right? So this is 400, okay, or 0.4 because we are measuring in megahertz, okay? So that's our next interferer. And then the channel spacing must tolerate an alternate adjacent channel blocker of 20 dB higher than the desired signal. So basically, this means that I can somehow, my filter must make sure that I can tolerate a difference between those two signals, right, in terms of level, that can reach up to 20 dB, right? Okay. Right, this is what we need to design our filter to make sure that this is still acceptable. Okay, and the question is calculate the quality factor of the second order RLC filter or LC filter, which is required to suppress this interferer. This 20 dB higher interferer needs to be suppressed by 35 dBs. So now I'm going to design my filter. Typically, the filter has to be flat within the duration of my signal, within the frequency range of my signal, and then it starts dropping before and after, right? And the idea here is, okay, I didn't draw this correctly, just to match the description. So let me do it in a better way. So here, right, that's flat during the signal, and then it starts dropping such that with certain, of course it's symmetric around the center frequency of 900, and the idea is at this point where the filter is affecting the peak of my interferer, it should provide a 35 dB reduction from the maximum value, which means that if I compare the maximum value of the filter to the value at this point, I have to have a drop of 35 dB, right? It's a reduction of 35 dB. This is all assuming that if I have a lossless filter, then here it has 0 dB value, which is a gain of 1. And then the gain drops below 1 as I go further. So it needs to attenuate the adjacent interferer by a factor of 35 dB. To proceed with from here, basically, what's a second order RLC filter? What's meant here is the parallel RLC circuit. So we have resistance, capacitance, and inductance parallel to each other. And remember, I'm not going to do the derivation here, but remember from your circuits that such a filter will have a Z, an impedance, which is a function of frequency. And if we want to put it in the form of the transfer function, we will put it as a function of the S, which is S is equal to J omega in this case. And it's equal to RL multiplied by S divided by RLC multiplied by S squared plus L multiplied by S plus R. So this is the impedance in general as a function of frequency. And for this filter, the center frequency is equal to 1 over the root of LC. And we know that this center frequency is the 900 megahertz, right? But don't forget that it's omega, not F, so it has to be multiplied by 2 pi, right? So we know now that 1 over the root of LC is equal to 2 pi 900 megahertz, which means that LC as a value, we can figure it out, right? So this means that we know from here what's the value of LC. We can put it as a number, L multiplied by C, right? Now we also know that for this filter, the magnitude, and what we look at here, this shape that we see here is basically the amplitude or the magnitude of the filter, right? And in terms of looking at filter gains and all these things, we should be actually looking at the magnitude square because we are looking at power values. So we know that the magnitude square, again, the derivation is not part of what we need to do here. You should be able to do this. The magnitude square of this filter is equal to, as a function of J omega, or S if you want, is equal to L square omega square divided by 1 minus L multiplied by C multiplied by omega square. This whole thing is squared plus L square omega square divided by R square. Okay. Now this square of the magnitude at the point of suppressing the interferer should be 35 dB lower, right? In terms of absolute magnitude, not the square. So in terms of the square magnitude, it should be equal to the square of the absolute value of 35 dB. So first, how much is a drop of 35 dB? 35 dB drop is approximately 56.2 in absolute values. You can do that in your calculator. So what we are saying is that the ratio between the maximum here of the filter response at the center frequency, right, divided by the value here at suppressing the interference at 900.4 should be the ratio between this and this in square magnitude should be 56.2 squared, right? So the ratio of the square magnitude should be so the Z, if I want to write this the right way, so the Z T at J omega naught squared divided by Z T at this desired point of J omega 1 squared, where this is my omega 1, right? This is the desired point of attenuation. The ratio between those two should be equal to 1 over 56.2 squared, right? But we know that Z at J omega naught squared is equal to R squared, right? Because at resonance, the L and C disappear. They cancel each other as impedances, and I end up with only a resistive impedance, right? So if this is the case, then this means that what I want to achieve here in terms of gain, what I want to achieve at this point in terms of gain, right? Square the gain, the power gain of the filter is going to be simply this maximum value, R squared, divided by the 56.2 squared, right? So this is basically the value of the gain at this point, right? The impedance at this point, the square of the magnitude of the impedance at this point should be equal to this number, right? At the point when I put omega equals to omega 1, when I put omega equals to 900.4 megahertz. Okay, now if this is the case, and I put this value, I can actually work out the equations that we see in front of us, such that I can get that L squared multiplied by omega squared divided by R squared is equal to some number. I can get that number by manipulating. So this is the equation that I have. This is the equation that I'm trying to solve. This one. This equation. Right? Okay. L square omega square over 1 minus LC omega square all squared plus L square omega square over R square is equal to R square divided by 56.2 squared, right? Okay, so I have to notice that I can get rid of this whole term by replacing it with values, right? Because I know what's the value of LC, as I mentioned here, and I know what's the frequency that I'm working at. It's 900.4, so I can get this to be a number, and then accordingly I can end up with L square omega square over R squared up here from this side, move to this side, and I have also L square omega square over R square, right? Both terms will appear up and down, and then I have a number on the other side, 1 over 56.2 squared, right? So a number plus this unknown and this unknown up here is equal to a number on this side, which means that I can solve to find the value of L square omega square over R square. Why do I want to find the value as is rather than looking for the L and R and so on? Because this value is a good representation of the quality factor that I'm looking for, which is the required here. So I will find by solving for L square omega square over R square that it is equal to approximately 2.504 times 10 to the minus 10. Hence, I can find my quality factor, which is simply R over L omega for this circuit. The quality factor is defined as R over L omega. This is basically the square root of the inverse of this number, right? So it's going to be equal to approximately 63,200, which is a very high quality factor. In order to achieve such a quality factor, you really need a very, very complicated and high values for your capacitance, inductance, and so on. So you will end up with an impractical circuit that you cannot really implement. Okay, a circuit with such a quality factor is really very difficult. Okay, and hence it's not really practical to just suppress the interferers. We cannot really do this. We cannot get rid of them. So what's really the practical solution in this case? Well, the practical solution is actually that we have to divide filtering into two stages. One of them is done at the very high frequency in order to maintain the quality factor required for that filtering to be reasonable value and the complexity and practicality of implementation to be within common practice. That filter, the first filter that we encounter, has to be with wider bandwidth. And typically we call that the band filter. For example, the GSM band used for the GSM serial system does not include only one channel. It includes multiple channels, right? All of them are within the band reserved for GSM operator, right? So in this case, we can have a bandwidth which is wider, which allows us to really get a reasonable quality factor at a center frequency of that GSM band, which is at 900 megahertz that we were talking about. So we only need in this case to make sure that we don't go into the band of another technology, right? Or another carrier operator, right? So that's one level, and this is called band selection filter. Then later on, after we do certain processing inside our receiver, we can actually focus on the channel selection filter. Again, we cannot do this channel selection filter at this stage because we are working here at a very high center frequency, so it's very difficult. So we probably need to bring our signal down to some lower frequency, bring this whole band to some lower frequency, and then we can do a channel selection to select my intended or desired user channel. Okay, since I came to a slightly lower frequency, now I can reduce the bandwidth without increasing the quality factor that much. Okay, now a few things to keep in mind, that when we are doing this operation of two stages filtering, the band selection and the channel selection, we have to make sure that all the stages in the receiver before the channel selection have to be sufficiently linear, because in all these stages before doing the channel selection, we still have adjacent interferers, right? So we have to take care of the intermodulation and the cross modulation and all these aspects that has to do with adjacent interferers, whether a single or more than one adjacent interferer, right? So linearity is an issue at this stage until we reach the stage where we have the channel selection, so we removed all the adjacent interferers and we don't need to worry about them that much. At that stage we can actually work with less linearity constraints. The other thing is we have to leave the channel selection as much as possible to the stages of lower center frequency, because otherwise it will still require very high quality factor, which is not practically implementable, as we discussed in the previous example. Now, most of the receivers, they do have a band selection filter, and for that band selection filter, what's really important is not the selectivity, so we don't need to drop very quickly, we don't need to have a very high quality factor as we said, but what's more important for us, not to have losses in the band pass part, in the part where we are allowing the signal to go through. Why? Because remember, when we cascade components, and our first component here is going to be the band selection filter. If the previous component has very low gain, again lower than 1, then this means that the noise figure of the ones that comes after it becomes amplified, because we divide the noise figure by the gain. Remember that the noise figure at a certain stage, right, stage I, is divided by the gain, the collective gain of previous stages. Okay, so from I minus 1 until we reach the first stage, right? So if I have a noise figure at a stage after the band selection filter, and the band selection filter has a gain which is smaller than 1, so it's very lossy, this means that the noise figure of the next stage is going to be actually amplified, which is something I do not want, right? So that's why the issue is, if we want to increase the selectivity of the receive band selection filter, this means that we need higher order filters. Higher order filters means more cascaded components. More cascaded components means more losses. More losses means we are affecting the overall noise figure badly. That's why we should not focus that much on selectivity at this stage of the band selection, but more into making sure that we don't have that much losses here. So it's as close to 1 as possible, right? With very low losses, typically in the range of 0.5 to 1 dB. More than that is going to be too much. Okay. Another important practical aspect to consider has to do with the general design of transceivers. There are two types of transceivers. There is ones that use time division duplexing. Duplexing means how do you divide transmission and reception time? Do you do them at the same time, same frequency, different times, different frequencies? What are the possibilities? There are two possibilities. Time division duplexing means that the transmitter and the receiver can use the same frequency, but they have to be working alternately. So your transceiver is either receiving only and it stops transmitting, or it's transmitting only and it stops, disconnects reception, right? That's called time division duplexing. The other option is to transmit and receive at the same time, and in this case they have to use two different frequencies, right? Otherwise they will interfere with each other. The transmitted signal is going to interfere with the received signal, and in this case we have something called, we have the band pass filter for the transmitter, for the frequency of the transmitter. We have the band pass filter at the last stage, at the first stage of the receiver. This is at the last stage of the transmitter. It's called shaping filter, or signal shaping filter, to make sure that the signal is bounded by the desired band. And at the reception side we have the band pass filter, or the channel selection filter, or the band selection filter, depending which one it comes first. And the combination of those two is called the duplexer, which is a combination of the transmit filter and the receive filter of the transceiver, right? As we can see, we are not dealing with ideal filters, and we can see some typical values here. And don't forget that these are going to be operating at the same time. So this means that basically the signal which is being transmitted from here is going to be attenuated, right? Signal being transmitted is going to be attenuated by the receiver, right? Okay, at this particular frequency, and the attenuation is in the range of 50 dB, for example. So let's see if this is the case. What's going to be the issue? So here is my low noise amplifier of the receiver. Here is my power amplifier. Assume that I'm sending a 1 watt, which is a 30 dB dBm signal through my antenna in the transmission band, and then I have the reception band here, and there is a leakage because the filter of the reception cannot really cancel everything coming from the transmitter. So the leakage means that this signal is attenuated by minus 50 dB, as we saw in the previous graph, and then it goes into the low noise amplifier in addition to my other received signal. But notice that 1 watt after going through minus 50 dB is still really a considerable value. Minus 20 dBm is going to be very much comparable to what I will receive actually, or even might be higher than what I will receive through the antenna. Typically, I receive signals here around minus 80 dBm, minus 90 dBm, right? So I have to take care of that as part of the design in the FDD systems particularly. That's called the duplexer design. Okay. So after taking those considerations into account, the filtering considerations for narrowband transmission, the fact that we end up practically using multiple stages of filtering. So we have the band selection filter, we have the channel selection filter, and there are practical considerations for each one of them, when it should be done, how it should be done, in order to achieve practicality and efficiency at the same time. After taking all these considerations into account, and similarly also the consideration of the duplexer and so on, we start now looking at different architectures of receivers. And the first receiver that we'll look at is called the heterodyne receiver. And the heterodyne receiver, or the basic heterodyne receiver, is a receiver that brings the signal to an intermediate frequency. It doesn't bring it from its modulated frequency down to zero frequency, or down to its baseband representation. It brings it to an intermediate frequency. The idea of doing this is to make sure that we can actually do the channel selection with less quality factor requirement, as we discussed in the previous slides, right? What does this mean? I have a signal transmitted over a carrier, which is called WN. This is the input signal carrier frequency or center frequency. Rather than demodulating it to zero, which means I should have multiplied it by cosine WN here, and that would bring it to zero, and then low pass filter it. What I'm going to do is I'm gonna multiply it by some local oscillator, which is different from WN. Now the end result of doing this, as you might already know, is I'm gonna have the signal appearing at WN minus W local frequency, positive and negative side, and also at WN plus W local frequency, positive and negative side. Now, since I'm doing low pass filtering, this means that I'm actually focusing only on this part, right? So I'm only cutting this part, and I'm actually suppressing the other ones. So the end result is I'm going to receive, or going to move my signal to a lower band. Now I can do a better selectivity in terms of channel selection, and I can actually suppress some of the local carriers around me that can in-band interferers around me or adjacent to me, so that I can deal with the signal more appropriately. Of course, the next stage might be bringing it actually to zero frequency, which now can be done since we have done our channel selection and removed adjacent interferers. So now we can bring it down to zero, or the baseband, the original frequency of the signal, without much consideration about nonlinearities. So now we can deal with the signal without much considerations of nonlinearity. Now, typically, the down convergent mixer in these designs is preceded by a low noise amplifier, so that the signal is brought up so that it can compete with the noise generated by the mixer. Mixers are, generally speaking, noisy elements in transceivers, and we'll see later one of the reasons why they are noisy elements. Okay, so don't forget that we typically have multiple channels within our transmission band, right? For example, the AM radio has a transmission band of several radio channels, right? starting with the minimum frequency and going all the way to maximum frequency. For example, the FM band, which is the FM radio band, starts from 88 megahertz and goes all the way to 108 megahertz, right? But in between those two ranges, or the upper and the lower band frequencies, there are different channels in the middle. Each one of them is a radio channel that you can tune and listen to. So now your heterodyne receiver, how it can be tuned to each one of those within the technology band or the used band. There are two ways to do this. The first way is that your local oscillator that you multiply the signal with is fixed. So as the incoming signal changes in terms of its center frequency, the intermediate frequency that you bring the signal to is going to change. So here for RF1, you will end up with IF1. For RF2, you will end up with intermediate stage 2 and so on, since your local oscillator has a fixed frequency. The other option, this is called the constant local oscillator. The other option is to actually make sure that any signal that you tune to is brought to the same IF. So if I tune to this one, I want to bring it to IF. If I tune to this one, I want to bring it also to IF. In this case, I have to change my local oscillator value so that the difference between those two ends up being the FIF. This is a more practical implementation, more common implementation, because basically it allows for fixing the frequency of the coming stages starting from the IF stage all the way until you go back to baseband. While this one would require all the all the coming stages after the local oscillator multiplication to be tunable to work at different frequencies. At one case they will work at IF1, in another case they work at IF2. This is more expensive, generally speaking, in terms of components to be used. Okay. So is the heterodyne receiver problem free, and it's very nice design, and it has all advantages, and everything is nice. It simplifies filter design, and life is nice, so everyone is going to work with heterodyne receiver because it has no problem? Not true. Cannot happen in engineering or in practice in general. What's the problem? The problem is that imagining that you have this local oscillator frequency, and this is the signal that you want to bring to the IF stage, right? The IF is going to be the difference between those two signals, right? Now, unfortunately, if there is another signal, which is, so if this signal is lower than your local oscillator, and the local oscillator is going to bring it down to the IF, if there is another signal which is higher than the local oscillator and exactly IF distance away from it, this one is also going to be brought down by the local oscillator to the IF stage. So you end up with those two signals, with those two channels interfering with each other. Both of them are going to be brought into the IF stage, right? And this is called the image problem, or the image issue with heterodyne receivers. And you have to work out around this. You have to make sure that you can overcome this problem, the image problem. Okay. To further describe what's going on, you can see here different scenarios of the position of the local oscillator with respect to the received signals, right? If I have a signal at omega 1, which is my desired signal, for example, and another signal at omega 2, which is kind of an interferer to my signal, what will happen if my local oscillator is below both of them? Then one of them is going to be brought into the IF stage, and the other one is going to be higher with the same distance between them, which is fine. I can now do the channel selection and get rid of this undesired one. Now, what happens if the local oscillator is in between the two? Now, being in between the two, but not exactly in the middle between them, what will happen is both of them, the lower one is going to be brought into the IF, but it's gonna be flipped as you see here, right? This is not the same as this one, because the lower one is brought up and the upper one is brought down. So now I end up with the positive band of the signal looking as an image, as a flipped one from the actual signal, right? It's flipped, right? But that's not the only issue. The other issue is now the other one at higher frequency became closer, which means that if I want to do any channel selection now, it's much harder, right? It's very close. Look at the distance here, look at the distance here. So this is in general an issue. Even if they don't interfere directly, the effect is gonna be bad. Now let's look at the third possibility. The third possibility is the worst case scenario, that it's exactly in the center between both of them. And in this case, the two signals are going to overlap over each other, right? And the lower one is going to be flipped, the upper one is going to stay as is. Now the other scenario is if the local oscillation is above both frequencies, so the two signals are going to be brought down. One of them is going to be at the IF, the other one is not going to be, and the distance between them is going to be maintained. But the problem is both of them are flipped, right? If you look at the positive band, both of them are flipped. They don't look like the original signal, they are flipped, mirror of the original signal, which is an issue that we'll discuss later. Okay, here is a small problem to look at the image problem, and a small example to look at the image problem. And it says that formulate the down conversion in figure below using expressions for the desired signal and the image. So we have a desired signal that we see here. We have an image that we see here. We have a local oscillator that we see here. Our local oscillator is multiplied by both signals, and then we go through low pass filtering. And this local oscillator is in the center between them, so this means that the image problem is going to appear in this case. And the question is, how do you write this in equations to see what's happening? Okay, so assume that the first signal, or the desired signal, is called, it's a cosine function, right? And it's called A naught, or A desired, if you want. So the first signal is A, we call it A incoming to be consistent with what's in your textbook. So A incoming signal, right, with some envelope, and it's multiplied by cosine omega incoming. It's called here omega incoming, yes, plus some phase shift in general, right? And the other signal, so this is this one, the other signal is some A image, some envelope, multiplied by cosine omega image multiplied by t plus some phase shift of the image, right? And in general, phase shifts, and even the phase shift can be a function of time as well. We don't know, right? That's the general form, right? Now, when these two signals added together are multiplied by the local oscillator, which is again it's a cosine function. So this one is A local oscillator multiplied by cosine omega local oscillator t, right? The mixer is simply multiplying these together, so you end up with cosine times cosine. We know that cosine times cosine gives you cosine the addition, cosine the difference, and there is a factor of half. So the end result is that you have the XIF signal is equal to half the input signal multiplied by the amplitude of the local oscillator multiplied by cosine, and in this case it's omega n plus omega local oscillator. And this is multiplied by t, both frequencies added together, plus the phase that we have in our desired signal. And then we have minus half an t a local oscillator multiplied by cosine. I prefer to do each term in one line because I cannot put them beside each other, right? So minus half an t a local oscillator cosine omega n minus omega local oscillator multiplied by t plus phi n of t, and then plus the terms that comes from the image. So half a image of t a local oscillator cosine omega image plus omega local oscillator t plus phi image of t minus half a image of t a local oscillator cosine omega image minus omega local oscillator times t plus phi image of t, right? Okay, now we see that we have a low-pass filter after that. So this low-pass filter means that those terms are gonna simply disappear, and after the low-pass filter I will end up only with this and this guy, right? These are the two terms that I will have after the low-pass filtering, right? That's it for this important note about the heterodyne receiver, and maybe you noticed it when we were discussing the image problem, is that I can have the local oscillator below or above my desired signal. In both cases, it's gonna bring the signal down to the intermediate frequency, right? With a difference of the sign, positive or negative sign, right? What's the difference between those two? Well, there are some practical aspects that in some applications makes one better than the other, and in other applications it's the opposite. Generally speaking, the super dyne, or the case when you have your local oscillator higher than the desired signal, is more practically better than the case of the infradyne, where you have your local oscillator lower than the desired signal. Okay. In general, because designing oscillators at lower frequencies in a certain range is more challenging in terms of the noise and some other aspects. Okay. So the heterodyne receiver, which is using superdyne, is typically called in the literature the super heterodyne receiver. And that's the most common heterodyne implementation that we see, using the superdyne, not the infradyne. Now let's look at this example. Designer of an IEEE 82.11g receiver attempts to place the image frequency in the GPS band because it contains only low-level satellite transmissions. So basically trying to pick the carrier, the local oscillator, such that my image, when I go to my intermediate frequency, my image is going to be the GPS band. And does this work? Is this possible? Why the designer wants to do this? Because the GPS signal is a signal that comes from satellite. It's a very weak signal. Um, Power is very low. So this means that I don't really care about the image in this case. It's gonna be very low signal compared to mine. So I can just tolerate with that. Is that possible? Now, the problem cannot be solved until you know the bands, and that's why it's given here in the problem, in the example. And the band of the GPS is 1.565 gigahertz up to 1.585 gigahertz, while the band of the IEEE 802.11g, which is your Wi-Fi, one of the Wi-Fi standards, is from 2.4 up to 2.48 gigahertz. So here we're talking about a bandwidth of 80 megahertz, right? While here we're talking about a bandwidth of 20 megahertz, right? Now, if I want to make sure that my band is imaged in another band, it has to be that the other band, which is I'm trying to make as my image, has to be either bigger than my band or equal to it. Why? Let's look at the situation. Now, if I put my local oscillator carrier in the center between the 2.4 and the 1.565. So the 2.4 is going to be imaged by the 1.565, and I pick the center between those two, and I put that as my IF band, right? This means that my local oscillator, and here we are talking about using fixed local oscillator. So assuming that I will put that local oscillator here, this is my FLO, and that one is going to map this to be the image of this. Now the next one is gonna have an image somewhere here, next one an image somewhere here, next one, until I reach the 20 megahertz bandwidth, which is at approximately, right, 2.42, right? And after this point, so if you go to exceed that one, all these points on that side will have images that go actually outside the range of the GPS band. So that's not doable, practically speaking. Another example here has to do with the effect of image on the design. This is from a different perspective. So assume that I have an 802.11g and an 802.11a. So dual band Wi-Fi transceiver. And the designer wants to use a single local oscillator so that those two bands can be actually demodulated to an IF using the same local oscillator. The idea is it has to be placed somewhere in between both of them, that local oscillator. So if you look at those bands, they span the 2.4 up to 2.48. That's the G. And the other band is 5.15 up to 5.825. That's the 802.11a 5 gig band. And if I choose my local oscillator to be somewhere here in the middle between them, this is my local oscillator frequency. The question is going to be, is this possible just to use one as an intermediate frequency demodulator for those two technologies in one heterodyne receiver? And if you do that, you will end up with some of these being images for some of these, no matter how you move it, right? And this means that practically this is not doable because one band is going to image the other, so they're going to interfere at the intermediate frequency. So you cannot really do such a design. Very simple argument, not much calculation, but just to get the sense of how these designs work. And as an RF designer, you have to take care of that, okay? So what's the solution for the image problem? Is it a problem that means that the heterodyne receiver doesn't work? No, there is a solution, of course. Intuitively, you should use some kind of filtering. It's called an image reject filter that allows you to subsidize the frequency range which is expected to be your image, which is the frequency range at 2 WIF away from you. So you design your receiver to work at a certain intermediate frequency. Accordingly, you know that anything which is double that intermediate frequency away from you is going to be an image for you. So you filter out those signals. Typically, the distance here is a trade-off. So if you use a high IF value, this means that this distance is longer, which means that this filter is easier to design. But the problem is high IF value means that still in your intermediate frequency, getting a channel selection filter with high quality is going to be a challenge because you will need high quality channel selection filter. And if you lower your intermediate frequency a little bit, this means that your channel selection design can be simpler, but then this means that your image is not that far from you. So you have to take that into account in terms of designing your image reject filter. So it's a trade-off between those two, the image reject and the channel selection filter. Typically, the image rejection filter is a filter between the low noise amplifier and the mixer. And the reason that it's put after the low noise amplifier because the existence of the amplifier lowers the contribution of that filter to the noise figure. And the image reject filter is required to be, rather than being extremely selective, it's more type of a filter that requires more linearity and less attenuation. Typically, the design of those image reject filters is done outside the chip using passive components. They cannot be inside your RF chip in most practical implementations. And the question is, can we actually put this filter before the low noise amplifier and use it actually as our band selection as well? Well, yes, but the problem is the in-band loss of this filter is very critical. And if that's for the band selection, and if we do that, we might end up with too much restrictions on rejecting our image. So we typically don't. We use another filter separate from this for the band selection, and then we put the image rejection filter. Then our signal is brought into the IF stage where we do the channel selection filter, and then our signal is brought down to its baseband. Okay. The trade-off between the image rejection and channel selection is quite obvious. So if you decide to use an image rejection filter For the case where your IF, your intermediate frequency, is high, then you can actually design a filter for image rejection that can really reduce the image value, so it becomes extremely small, right? But the disadvantage is because you are working at a high frequency IF, it's very difficult to actually design a filter that will reduce your adjacent interferers channels, right? The opposite to that, if you decide to work with lower values of IF, now this means that the distance between your signal and the image is going to be smaller, and typically the filter is not going to attenuate this image too much, so you'll have an image interference, but your intermediate frequency is low. You can design a channel selection filter which is very selective, right, without going into extreme values for your uh, quality factor. So it's a trade-off. So higher intermediate frequency allows better rejection of images, but makes it more challenging to remove adjacent interferers during channel selection. The opposite, lower intermediate frequency, means that image rejection is gonna be not that much, so lower, but you can do a much better job in terms of channel selection. Okay. Now another thing is heterodyne receivers, they can actually come into multiple stages, so it doesn't have to be a first stage and then after that you go to zero or you go to the baseband. It can come actually in multiple stages. The most common one is a dual stage heterodyne receiver. So you have your signal coming from here, goes through the low noise. This is the band selection filter, low noise amplifier, band pass filter for image rejection. Then you go through the first local oscillator, you bring it to a first intermediate frequency, IF1, after band pass filtering. And then you actually do some second intermediate uh, brought down through a second local oscillator to IF2. And here at this part, you do actually the channel selection of your channel. Why we do the multiple stages? Because it might allow us to use still wider filters in the first stage. And then in the second stage, when we do the channel selection, we go really to low IF, so we can do really a very good job in terms of channel selection. Again, it's a complexity versus quality trade-off. So you add more stages, but the idea is you can do a better job in terms of removing interferers. This just shows you at different stages how the signal looks like. Not gonna really go point by point on this. You can actually, given the information that we studied before, review this stage by stage. The whole idea here is that you will encounter the image problem twice. So don't forget that that you will encounter the image problem 2 times. Okay. When you go to the first intermediate frequency and then when you go to the second intermediate frequency. Okay. Here's an example of dual down conversion. You have this dual down converter, and we are assuming that in all cases we are using low side injection for both down conversion mixers in this figure. And the question says determine the image frequencies based on your signal frequency and the local oscillators. So let's do it stage by stage as we learned, right? So if you go through the first stage here until you come to the intermediate frequency, the first intermediate frequency, what you encounter is going to be your incoming signal, right? Your local oscillator, which is lower because it says that we are using so this is WN of the incoming signal, and your um, image is going to be uh, at an equal distance from here. So that's your image. Just show the image with blackened one. And the image, the first image, is actually at 2W local oscillator minus. So this one is going to be at 2W local oscillator 1 minus W income, right? This is the value of your first image location. Okay, now your signal now is going to be located at WIF 1. So your signal in this case is going to be located at the difference between those two guys, right? So your current, we go after this. So the second stage, your signal, your actual signal is going to be located at WN minus W local oscillator, right? 1. That's the IF1 stage where the signal has become. You are using now another WLO2, and your image should be again same thing, same distance from this guy, right? So it should be at W image 2, which is given by the expression 2 W local oscillator 2 minus W N minus W local oscillator 1, right? That's it. So we figured out the locations of the two images, so the second image and the first image. Nice. So the summary of what we did today is that we looked at some of the practical aspects in receiver designs in general, particularly the narrow band and the filter design complexity issue, the band selection and channel selection filtering, and the TDD and FDD with the associated duplexer feed-through issue. Okay. Now, after looking at these practical aspects, we move to the first architecture that can solve some of these aspects, even though it introduces its own challenges, which is the heterodyne receiver architecture, the one that brings the signal to an intermediate frequency and then do the channel selection at that point to make the channel selection much easier, the rejection of the adjacent interference much easier. Then the heterodyne itself creates a problem, which is the image problem, and then we solve this problem using the image filter. There's another solution to this problem that we'll explore in future lectures, but then the image filter itself has some challenges of its own in terms of designing it, and particularly we looked at the problem of the trade-off between the image filter and the channel selection filter depending on where you select your intermediate frequency, and then we looked at more practical solution to the filtering issues and the image rejection issues in heterodyne receivers by looking at multi-stages, particularly the dual IF or the dual down conversion architecture. What will we do next time? We'll look at mixers and the problems that they create. I told you that they are noisy elements of your transceiver. So we'll look quickly at one famous problem of mixers called the mixer spurs. And then we'll look at some modern heterodyne receiver architectures that solve some of the existing practical issues, particularly the zero IF and the sliding IF architectures of heterodyne receiver, or modifications or updates to the heterodyne receiver architecture. And then we will look at another completely different architecture, the direct conversion, the one that we have been learning about without really discussing its issues. Um, Now, as you see, the direct conversion has its advantages, but you can see the list of problems. That's why initially the heterodyne receiver was the choice, but then later on the direct conversion became the kind of the standard for receivers nowadays in modern communication systems. Okay, thank you.